Hi, I'm Boon Kiat and I'm a postdoc working at Seoul National University. I would like to thank the organizers for allowing me this chance to talk about my recent work on machine-assisted exploration of simulation parameters. My collaborators are Hong Jun An, Eunjin Shin, and Ji-Hoon Kim from Seoul National University. So as we are all familiar with, our universe is made up of dark matter and baryons. According to the primordial density perturbations, the dark matters would form the gravitational potential wells or halos, and it will start to pull in more dark matter, which leads to the growth of the dark matter halo, as well as the baryons falling in would initiate a series of baryonic processes such as star formation. So we attempt to capture all this structure formation and evolution using cosmological simulation. So in these simulations, ideally we want to cover the length scales ranging from the event horizon or the black hole to the size of the observable universe, which is 15 orders of magnitude difference. This is impossible for even state-of-the-art simulations to cover. And so we resort to using subgrid models for scales that we cannot resolve, such as for star formation or for feedback. So in order for our simulations to mimic the actual universe, there's a need to calibrate our feedback. And one such work is done by O et al. In 2020. And the figure that you see there is the result from the paper. It is calibrating three feedback parameters, which I'll talk about later, indicated by the different colored arrows. It's trying to calibrate the baryonic makeup of a Milky Way sized halo at redshift 0 using the FS and FD, which I also talk about later in greater details. So what they did is they changed each parameter individually in order to find out the effect of the impact of the parameters on the actual observables. So they took a total of 71 simulations, and each simulation took about a day to reach redshift 0. So this means that they used over 2 months in order to calibrate this simulation. So what we are trying to do is to introduce the use of machine learning techniques in order to reduce this amount and hopefully get a better match than what they have achieved. So the parameters that they used to calibrate their subgrid models is actually based off the Chen and Oestreicher model. So they use the star formation efficiency, the feedback strength, and the feedback volume. So the feedback volume is something that ENSO allows for the user to change the volume in which the feedback energy is being injected into. So it can be a cube or it can be just the cells adjacent to the star particle. So they use these three parameters in order to calibrate the baryonic makeup of the halo at redshift 0 using the FD and FS. So FD is basically the ratio of the baryon mass to the universal baryon fraction multiplied by the M500, which is the mass contained within a radius of 500 times the critical density. And similarly, they looked at FS, which is just the analog for the stellar mass. So that's these observations are being produced by McGaw et al. In 2010, and they have it for a series of halo mass, but they are focused on a Milky Way sized halo. So we attempt to use our machine learning technique for this feedback calibration. At the same time, we want to show versatility of the machine. So we use a different problem, such as code comparison, which everyone should be familiar with. So the code comparison is basically looking at the discrepancy between grid-based code and particle-based code. So we use the result from Shin et al. 2021 to illustrate this. If you look at the leftmost column, it's the metal distribution from a grid-based code. The middle column is the metal distribution from a particle-based code. And what we see is that there's a difference between how the metal is being distributed, especially in the second, third, and fourth row. So what the authors did is they changed the diffusivity and the feedback energy budget used in this gizmo simulation. And you can see on the rightmost panel, rightmost column, the actual output is getting closer to the particle-based code. Sorry, closer to the grid-based code. So it's trying to resolve this discrepancy. So for our case, we will be also using this diffusivity and feedback energy budget to calibrate the stellar mass. So we'll compare the stellar mass, halo metal mass, halo gas mass within a certain metallicity from the gizmo simulation to that of the ENSO simulation. So the halo metal mass, the halo gas mass is specified within this particular range of metallicity because we found that the authors found that the diffusivity of the diffusivity used in the simulation is very highly influencing this halo gas mass. So machine learning has been used for a wide range of problems in astronomy, such as denoising astronomical images and down to cosmological models, parameter estimation. So you can see those previous work on the right-hand side. So we are now trying to apply this to the simulation. So we are using a technique known as active learning, where there's interaction between data generation and the machine. So essentially what it's doing is we'll feed the machine with a set of data. The data would consist of the parameters and the output. The machine would digest this and we will tell the machine to give us a set of parameters that will give a certain output. So then the machine uses this, our instruction or our target, and then generate a set of parameters that we can use for our simulation. Then we will actually run the simulation and then feed this simulation and its corresponding output to the machine itself. And this cycle continues until the output from the machine is within certain tolerance level. So the machine makes use of neural density estimator. What it does is it represents the output with a range with a mixture of Gaussians. So the Gaussians are represented by the mean and the standard deviation. So we use multiple Gaussians to represent the output. And we are minimizing the loss function, which is the cross entropy function used in our machine. And we found that reinitializing the network weight of each iteration would actually help the performance of the machine. So what this means is when we run a training set through the machine, the weights that the machine used to match the input and the output will be reset, will be given a fresh reset by the next iteration. So even though we use this strategy, there's also other hyperparameters that we need to calibrate, such as the number of Gaussians we want to use, the number of input data, and the number of additional data that we give to the machine per iteration. So in order to do that, we use a well-defined problem, which is the projectile motion with air resistance. So it's given by the equation that you see on the slide. And what we are varying is the velocity in which we throw the projectile, the angle, and the drag coefficient of the object that we are throwing. And we are hoping that the projectile, it was chosen randomly, but we want the projectile to have a distance of 2.3 meters and below a maximum height during the projectile of 0.6 meters. So like I said, we tried with the number of initial data, number of Gaussians, and number of accumulated data, which is the number of additional data that we give to the machine per iteration. And the results you can see on the right. We find that the number of initial data is actually 5 is the best amount for the simulations to reach within 5% error of the target. And the number of Gaussians is 20. And the last parameter is the number of additional data that we give to the machine. We limit it to 1 and 2 because we want to mimic the actual situation of running a simulation where the additional data that you are giving to the machine would be restricted by the computational resources that you have. So we found that 1 is actually the best performing. So using this machine with these hyperparameters, we apply it to the feedback calibration, and we found the feedback calibration, the optimal is being found within 22 simulations. So you can see in the plot there, the black region is the initial training data. The yellow region is the behavior of the machine after the best match is found. So we will talk more about that later. But this is this shows that we can actually use the recommendation from the machine to get a optimal. And how we define the optimal is using the difference between the FD of the simulated and the observed galaxy. So on the top panel, that is what it is. And on the bottom panel, it is the difference of the simulated and the observed galaxy, the FS of the galaxy itself. So you can see that to the green line and the blue lines are the levels of agreement that was found in the Ho et al. 2020. So we find that the machine given recommendation is actually giving us a better agreement. As you see from the FD, it is a better agreement than what was being presented before. And this is being done in 22 simulations, which is a factor of 3 savings, or more than 3 to be specific. So not only did the machine find a good set of parameters that's able to replicate the actual universe, it did so much faster. But as you can see from the yellow region, after the best match is found, the machine actually didn't focus on the area that gave the best outcome. So it went back to widely varying. You can see both in terms of the parameters as well as the outputs. So this large variation in the parameter is actually caused by the strategy that is being used. So as I've said, we actually represent the output using a whole bunch of Gaussians. So this machine would use a random seed to determine out of which Gaussian to give the recommendation. But that will also mean that there is no consideration of the probability. So in one instance, it might focus on one Gaussian and give a recommendation based on that. In another instance, it might go to a lower probability Gaussian and give you a recommendation based on that. So there is a consistency issue that we want to investigate, and that will be done when we change the strategy. So we are going to implement a strategy that takes into account the probability of the Gaussian distributions. That will be presented in the full paper that we are going to submit. But the aim here is to showcase the capability of this machine calibration. So machine-assisted calibration. So we will move on to the next project, which is the code comparison. So in this code comparison, we wanted, again, to remind you we wanted to resolve the discrepancy between the code, grid-based code and the particle-based code. So using the diffusivity, which is CD, and the feedback energy budget. So what you see here is that the diffusivity, the CD, is actually oscillating between 2 Gaussian peaks, because the behavior of the red crosses, they are centered around two distinct regions. So we find that in order to resolve this, we had a human intervention by taking a value somewhere in between to show or to try to tell the machine that the optimal is not within these 2 peaks. And you can see after the human intervention, we got the best match. And like I described earlier, it's based on the metal mass, the gas mass within a certain metallicity and the stellar mass. So it is so the blue line here is the target from the ENSO simulation or the grid-based simulation. So we found the optimal within 14 simulations, and the diffusivity found is actually 10 times that of what Shin et al. Found in 2021. So it means that there's actually discrepancy in the result that the subgrid model is presenting. The same thing can be said for the feedback calibration. The set of parameters that's being recommended by the machine is not actually not identical to the one that's found previously. But nonetheless, we obtain a good match to the target in both experiments. So in that sense, we've presented a novel technique using machine learning for application to different purposes. In our case, we showed it for feedback calibration as well as a code comparison. And it helped us identify discrepancy in parameters, meaning there's more than one combination of parameters that can give us a good match. And this would point to the limitations in the implemented model, either in the number of degrees of freedom that we are considering or in the model itself. The good thing about this machine is that when we start to calibrate the simulation itself, it provides a region for us to focus on. So if we remember the human intervention, if we were to include the human intervention, so if we have human analysis of the result together with the machine, we can potentially get huge saving in computational resources. So this future work would include applying this technique to other problems, such as simulation with black hole physics, because it is very expensive to run those simulations. And if you want to calibrate this kind of simulation, you don't want to spend too much resources on this. So using the machine can help. And of course, we can try different strategies, like I said, the human intervention, or we can try taking into account the probability of the actual Gaussian distribution. And finally, we can optimize the hyperparameters that's being used in the machine, because as of now, we've only used it based on a very simple projectile motion problem. That's the end. Thank you.